So here, maybe before going on, I will may start by recalling where I ended up yesterday, and I realized I didn't fully introduce the questions they constructed. I stopped just before the end. So maybe let me recall what I explained. So take X complex manifold. So there is this space I called BK, which is the blowing up of the K-jet space at the zero section. And in that space, you had, well, two things, maybe three things. The exceptional divisor, which is the isomorphic to the projectivization of K copies of the tangent bundle over X. Inside this exceptional divisor, you had this which is itself isomorphic to the projectivization of just one copy of the tangent bundle. And this Z mean lies in an open subset, U mean, and there is, as I explained yesterday, also a projection which goes back from U mean to Z mean, and actually going back from BKX to the exceptional divisor, restricting this way to U. And I told you that if you consider now the reparametrization group, GK, which is a semi-direct product between its unipotent radical and C star, well, you had a good quotient of U mean, a geometric quotient, sorry, of U mean by this unipotent radical UK. And here, the projection, going that way, induces well, a morphism between these quotients and Z mean with fibers isomorphic actually to C to some power, which if you count dimensions is 1 plus n minus 1 times k minus 1. So if you wish, you can look at that in coordinates. Okay, maybe that I will write that here and there. So this mean, as I said, is isomorphic to the projectivization of the tangent bundle. It is the space I will usually denote by x1. And if you take coordinates, say z1, zn on x, then you have several open charts on this projectivization. And for example, in the chart z1 prime different from 0, I will maybe write that here, you have the coordinates zj prime divided by z1 prime on this projectivization. And here in U mean divided by UK, you have all these coordinates plus some vertical coordinates, which are z1 prime. Maybe this is the one, which is over there. And also you had the coordinates, which I denoted by C P1 J, with P larger than 2 and J different. Right, maybe let me recall what the formula is for these coordinates, but I just want to emphasize the fact that these are vertical coordinates on the fibers of this morphism. So as I said, you have this formula for this. I will stick with 1 here, or maybe, okay, I will write I. But if you're lost somehow, imagine that I put a 1 to simplify it. Okay, so this is zi prime times p minus 1 times this thing that I wrote, Zj rho Zi inverse derivative p times at 0. Another way of writing that is to do it that way. So these are very classical coordinates. They appear in several important ways when we are considering the invariant jet differentials. And a typical formula for this is this one. So you iterate the operator given by dividing by z prime, z1, zi prime, and you do that p minus 1 times on this fraction. All right, so it gives you a long formula with higher order terms given by some Wronskian term, which you can write that way. So Zj derivative p times divided by zi prime, and then you have the counter term plus some lower order terms. And here you see that these terms actually belong to the ring of coordinates in the Brownian in BKX, the ones that I introduced yesterday. Okay, so also if you look at this expression, you see that this, for the standard action of C star on jet differential, has weight p minus 1. And actually, now if you want to obtain a projective space lying above, say, x or z mean, you want to quotient that further, not only by the action of UK, but also by the action of C star here. And that's how you obtain the Bérczi-Kirwan compactification. So I can do that here. All right. So maybe let me give a name to that quotient. Okay, I will do that in that place. So LK divided by UK, so it's a fiber bundle over Z mean with fiber affine spaces like that. I will call that LK. And it's lived above X1. And now what you can do is to take LK and remove from it the image of Z mean. Well, the thing playing the role of the zero section. Okay, so what this image actually is given by the vanishing of these coordinates if you look at them inside the fibers of this projection. So what's that mean? And this you can quotient by C star by giving with the following weights for the vertical coordinates. So to zi prime you give weight 1, and to this psi p ij you give weight p minus 1.
I have a basic question
Yes.
from the previous board. You say lower order terms. What are lower lower order derivatives? What do you mean?
Yeah, exactly. Sorry, lower order derivatives. So here, these are the only terms where you have a p derivative, p order derivative.
Thank you.
But all these expressions, so all the terms that appear are homogeneous of degree p minus 1 if you consider the standard action of C star on each of these coordinates. So these have weight p, these have weight 1, and if you rescale them, if you reparameterize them at the source for the action of C star, you get p minus 1 for the whole term. And then this is none other than the non-reductive GIT quotient that is constructed by Bérczi and Kirwan. maybe let me state a theorem to. Well, I will rewrite the things that I wrote just above, but in a slightly different manner. So on the space x1, so remember it is the projectivization of the tangent bundle. This is also Z mean. You can consider the following algebra of OX1, a coherent algebra of OX1 with some grading, which is generated. So on the chart zi prime different from 0 by say zi prime and this psi. And again with weight 1 d minus 1. So these algebra, they glue together over x1, and then you can see them as formal algebra if you want. And then you get, if you projectivize this algebra above x1, you get a projective space lying above x1. And it sits above the first stage of the Okay, so do I want to say something else? Yes, maybe let me say here that the fibers are then weighted projective spaces. So what are weights? Well, these are written here. So first you have weight 1, once. And then you have weight 1, a n minus 1 times. Weight 2, again, n minus 1 times, until weight k minus 1, also n minus 1 times. Alright, so you have this space, and it comes, if you describe it that way, with an orbifold tautological line bundle given by the standard tautological bundle associated to this algebra. Let me say that, as I said yesterday, note the OK1 constructed above is not the same it's not the OGIT1 that is constructed in the original article, because the way that this OGIT is constructed is by using some linearization on the space you start with, actually on PKX, in such a way that you actually can get ending up with some twisted version of this OK1, and it's, I think, a non-trivial matter to relate the two. I think it would be a very interesting question to really settle. But here in the rest of the talk, I will focus on that one. And in the end, I will explain to you what these residue formula permit to say about the intersection numbers that you want to compute with this line bundle. Okay. And also, let me say that I explained also yesterday that what we want to have in the end is some tautological line bundle whose sections give you symmetric, or not symmetric, but holomorphic jet differential equations on X. And if you look at sections of powers of OK1, you see that actually they have a denominator in Zi prime, for example, in this chart Zi prime different from 0. So sections of these do not give you right away jet differential equations. You have to twist them to have such a thing. And but it is quite easy to do. If you look at, say, sections of powers of OK1, I will write such a power already here. And then, if you want to clear the denominators here, you have to pull back the O1 on X1. And then after that, if you do that, pushing down the sections, maybe this is not the same by K. Let me call it rho K. If you push everything down, you end up with what you wanted, namely sections downstairs and even invariant ones. Okay, so maybe this O1 is not the best suited to study, but rather a twisted version, and this is actually what they do in the article. They have a better twisted version rather than this one. So keep that in mind. The OK1 that I have introduced is not directly the one you want to use in the end. You want to twist it to have holomorphic differential equations downstairs. Okay, so now what I want to do is to give you some other indications on these jet spaces and to explain to you why they are well suited to do intersection computations in a way that it is maybe closer to the things I usually understand and which are not related directly to non-reductive GIT. So here, maybe take what I'm going to explain with a grain of salt, because this is just an attempt of my part to understand somehow topologically these spaces, and namely from the point of view of deformation theory, to understand why you can do intersection theory in them, using, for example, data on X concerning the Segre classes of the tangent bundle. So I will write intersection topological, say, consideration on these spaces. Okay, so one thing you can do when you have jet spaces, and this is something which already appears with Green-Griffith jet differentials, is that you can deform them to end up with a true vector bundle, so on X. So there is a deformation. Maybe I will take a little bit more space to write that down. I'm not using the board in a very consistent way. So there is a deformation of one parameter deformation lying above C of the space JK. So this deformation, you can see it as lying above X times C, and it is in such a way that if you take any point in C different from 0 and look at the fiber above it, well, here you have X times this singleton. I will just write X. And here you have the Kth jet space lying as a fiber. And if you look at 0, well, you just have a direct sum of copies of the tangent bundle. So yesterday, if you remember, I wrote at some time, locally on X, we can assume that JKX is a sum of copies of the tangent bundle. Looking at some trivialization. Here what happens is that there is a deformation which is locally trivial on X, which allows you to deform this space, which is not a vector bundle, to a legitimate vector bundle. And now you can do all this construction on that space, on each fiber on C. And so you can deform every data that I have introduced over there to that space.
So the information is just coming from the grading?
Sorry?
Just coming from
Exactly. So this is the Rees deformation given by the grading, the standard grading on the Green-Griffith algebra. And it is not the, sorry, it is not the grading M, of course, but there is a standard filtration on that space. And if you take its graded object, this is just the sheaf of algebras that you have on that space. So if you want, if you are not very familiar with that, you can look in the Maïs notes. For example, he gave a conference in some lectures in Hanoi, so in that paper this is very well explained. All right, and so now you can deform every data which is introduced over there. So BKX, what order, containing U min, containing Z min, deforms to the central fiber, to some objects, which I will denote with a knot here. So this BK knot is just the blow-up at the zero section of this sum of copies of the tangent bundle, and in it you also have this U min knot containing the Z min knot, but the Z min knot actually is still the same as the Z min. It's not hard to see that if you blow this along the zero section, then the deformation is actually trivial when you look at it. And also, when you look at the exceptional divisor, nothing deforms. It's only the U min which deforms, and of course the total space. Okay, and so what is this U min knot? So this time, what I wrote yesterday only locally on the base will hold globally somehow. So this U min knot is the set of pairs in the blowing up so this belongs to the projectivization of the tangent bundle k times, and this belongs here to the tangent bundle k times. All right, so this is the set of pairs which of course are parallel, and such that this W1 is different from 0. Okay, I claim that this is actually the total space fact U min knot identifies with the total space of the, so it lies above the x1, the U min knot still lies above the Z min knot, which is still the x1, and this is the total space of this O minus 1 times the pullback of the tangent bundle, sorry, k minus 1 times, but you have to put a twist here. So how can you see that? Well, I'm just going to write a quick formula. So start from a pair WV, and then send it to a data which is completely equivalent to the first one. So to obtain this data, you just have to remember the V1, which will lie in the O minus 1. And you just also have to remember the W2, Wn, because the V2 and until Vk will be determined by the data of V1 and the Wi for I larger than 2. And so the Wi, you can see them as a morphism from the O1 to the tangent bundle, the pullback of the tangent bundle. Why? Because simply they permit to determine a morphism which takes lambda v1, or if you want, lambda w1, and send them to lambda w1. And so you have this identification, and you can plug that in that slot if you want, quotiented by UK, and you will be doing the same thing. You will have a fiber space above this projectization, and here I claim that you have done what in so this is a version of what is called so I think you call it linearization in the article, or maybe so. This is there is several different ways of seeing this risk deformation, but one thing you can do is to here I'm doing that to reduce the topological intersection computation to a computation on that space, rather, or the version that is obtained from it, by transforming this space in vector bundle over X. And so what is done in the article, rather, this is very similar in the idea, is to use the classifying space for the diffeomorphism lying above X, and actually do some sort of computation above a fiber and then pulling it back to X. And here there is a way of saying that you can do the computation on a different space, the one I'm trying to detail now, on a different space but which still gives the same intersection computation. And in the article, what they do is to do the computation on the classifying space and then pull it back to X. This is the idea is quite similar, actually. It's another way, I think, of presenting the idea. Okay, and so now I claim that if you take the quotient, so here, maybe a grain of thought here, but I claim that if you take this quotient with the U-min naught, there is another deformation to the total space, this time of O minus 1 plus the relative tangent bundle K minus 1 times. So here, look at what I am doing. I have a first deformation of that space to this sum of copies of the tangent bundle, and on that space, you can do the same thing as before by putting nodes everywhere, and you get new deformation sitting above C of the Bérczi-Kirwan jet tower. XK BK, deforming it into something which I will call XK BK, maybe not. And here I'm trying to do a new deformation on that new space, something which is somehow described in even more linearized terms. And so to do that, I claim that this X naught divided by UK deforms to that space. And to see that, the idea is, as before, trying to use some grading on the space, some grading on this algebra, rather, and deforming this grading to obtain a new algebra, which is actually the algebra associated to that space, to the sheaf of algebra on the total space lying above X. And so, to see this, what you have to do is to do the following thing. Say, imagine that you want to change coordinates between the chart 0, Z1 prime different from 0 and Z2 prime different from 0 lying in X1. So on that two charts, you have the coordinates which I have introduced over there, Z1 prime and the psi ij, and similarly on the chart Z2 prime. Well, I claim that if you want to express the change of coordinates, well, you can express, for example, the psi p1j in terms of the psi p2k. So you will have in the expression of the change of coordinates, first some linear expression, and here you will have some matrix, plus some lower order terms. And here the matrix is, you have to do the computation to see that. It is the same matrix that gives the change of coordinates between standard frames for these parts of the vector bundle. Namely, the change of coordinates between zj prime divided by z1 prime and z k prime divided by z2 prime. And now, if you scale these lower order terms, which is quite exactly what you do here to deform that to this, well, you will deform this uk mean divided by this u0 mean divided by uk, which have this coordinate plus the z1 prime, to that space. And of course, the O-1 here counts for the Z1 prime. Z1 prime is the coordinate of O-1. Right. So this is some computation you have to do, and then you get a grading filtration on the algebra QKM, whose graded terms is the algebra on that. Okay, so again, I'm in process of writing down, but I wanted to say that to say the following. Eventually, you end up being able to deform in two steps, if you want. This space to something which lies above x1 again. And here I can still put this fact also here. And on top of that, you will have the projectivization above x1 of the sum of O-1 plus some copies of the tangent bundle up to order k-1. But here, again, this is the projectivization you have to do is not a standard one, it's a weighted projectivization. So I'm usually writing that down as by putting some power here. I mean that this has weight L for the action of C star that you use to construct this projectivization lying above x. And what I want to say is that if you want to do now computation of intersection numbers related to the topological line monode on that space, you can do them on that space and end up with the same intersection numbers. So,
but the claim is that they are homeomorphic.
So,
the flat deformation.
Are there homeomorphic? I think they are. Yeah, and it is also so. This is a two-step deformation. So the first one is locally trivial above x. The second one is locally trivial above x1. But yeah, maybe I don't want to be too categorical about that. It doesn't really matter if they are homomorphic. The important is that they are. Yeah, this isotopic. Okay, but now I'm going back to what is actually done in the article, is to say that if you want to compute intersection numbers on that space, you can also, and that is what is done in the article, use equivariant cohomology. But on that, I will not be able to give you a lot of details. So I apologize in advance. But maybe let me explain why do we care about these intersection computations, because I think it has not been done really clearly yet. Intersection computations. So, if you recall, what we want to prove is that if you look at the tautological line bundle, well, O1 GIT this time, at the nth stage of the tower, and not only at that, but actually at the negative twist of it, if I'm not wrong, is that one where x in Pn plus 1 is a hypersurface. Well, we want to prove that this line bundle, this twisted line bundle, is bigger. To apply the strategy of slanted vector fits. And to do that, we use, well, the community, use the theorem, classical theorem, which is due to many people in different versions, but I think to pursue Japanese domain. The so-called algebraic Morse inequalities. Well, what does this theorem say? Well, pick a complex projective manifold, X, and a line bundle on it. Line bundle on a complex projective manifold. The goal of the theorem is to prove that L is big, and it gives a criterion for it. And the criterion is that you must first be able to write the line bundle as a difference of two Neff line bundles, and then to compute some intersection number. And so that's how we get, in the end, to these intersection computations. So if L is actually the line bundle associated to the difference of A and B, where A and B are Neff, this is the first thing. And second, if when you compute A to the top power, so let me call the top power small n, and you do that, and you remove n times a minus 1 times b. So this is some integer. Well, if this number is positive, then L is big. So the way to prove that thing is to actually first pass to the case where A and B, say, are very ample. This is not hard to do by simply removing or adding some E and B here, well, H maybe. So that A and B becomes ample, and then pass to some sufficiently high power. And then there is, you can write some exact sequences to end up proving that if you look at the H0 of the powers of M, then it goes like M to the dimension of the variety, which is one definition of B. Okay, and so here, if you want to apply this to the problem that we are considering, you first need to write down the O1 GIT as a difference two Neph-line bundles, and this is where a very important proposition in the article appears. Well, Bérczi-Kirwan proved that the OK1 deconstruct. So, okay, let me write it down and maybe give some more details about that in a minute. But they prove that the O1GIT, if you tensor it by the O2 of the hypersurface you are considering, well, you get a Neph-line bundle. Okay, so I'm cheating a bit because, strictly speaking, what Bérczi-Kirwan called O1GIT is not exactly that one. If you use the notation of the article, they use, well, the O1 they consider is actually some high power of this O1 there, namely the nth power of the O1 I am talking about. Here I'm rather talking about an orbital version of the O1, but I believe, so in the article, I believe the relevant object, if you want to do the computation, is to take the nth power, the nth root as an orbital line bundle, say, of the one that appears in the article, but it doesn't really matter in the end. And now you can introduce the A and B. So you can take A being actually this one, and B, it will be OX n minus 3 plus 2, and minus 1. And the second step is to compute that intersection number with, here, instead of n, you have to put the dimension of the kth jet space, of course. All right. So maybe let me say this orally. If you want to prove that such a line bundle is Neph, you can also do it if you have such a deformation over there. Because here, once you have a deformation like that, the tautological line bundle, OK1, also deforms to its counterpart here. And so if you manage to prove, for example, that the OK01 tensor some twist, say, coming from both stages, so if you manage to prove that such a thing is Neph, then Nephness carries to the deformation, because actually the deformations that you get to pass from here to there are constant outside the central fiber. So Nephness has a semi-continuity property, which makes so that if you have Nephness at the central fiber, it will be true also almost everywhere outside. But these deformations are constant outside the central fiber. So you get for free Nephness outside, and then you can do that on the two steps of the deformation. And this, well, I will let you do the exercise, but if you have this deformation, finding A and B such that this becomes Neph is something which you can do rather easily. For example, you just have to find A and B such that this line bundle is actually globally generated if you take sufficiently high power. So you can write down sections to have global generation. Okay. And so in the last 15 minutes, I will write down how you end the proof. So computation of this number. So A to the top power, nk here is the dimension of the space xk bk. So again, I will not be able to explain you the residue formula that appears in the work of Bérczi-Kirwan, but let me just say the following. They have a residue formula which allows you to compute, for example, the top intersection of the O1GIT on the total space. And this, I will not write down the complete formula, but I will just say that it is a residue, two-step residue, of some rational function in the formal variables, z and w, and the churn roots of the tangent bundle. And if you compute the residue, you can do that. Well, you can compute it so as to rewrite the formula as follows. So you will end up with an integral above x of some sum of product of Segre classes downstairs. So SPI indexed by some SPIs. So we are on the k jets bundle, so I think you have k minus 1 here. And so the sum is our all integers which sum up to n. And here you have some coefficients depending on P0, P1, and Pn, of course. Pk minus 1. And just for completeness, I'm going to say that it also depends on some parameter epsilon, which is related to the way that O1GIT is constructed. So this epsilon is related to the fact that if you want to construct this line bundle, you have to use a so-called well-adapted twist of the action of C star on the first JKX. And this well-adapted shift depends on some parameter epsilon that eventually appears in the formula. Yes, Frederick. Yeah. Thank you. All right, and you have such a formula expressed in terms of the Segre classes of the tangent bundle. And once you have, so this you can do also, I have expressed that for the top intersection of the O1GIT, but if you plug that in, you plug the relevant formulas inside the intersection number I wrote upstairs, you will end up with the same thing, similarly looking formula. This will look the same in the end, but of course with different parameters. So I'm going to write that quickly. So you have such intervals. And here are some new coefficients. All right, so if you want to compute this number, you want to apply it to a hypersurface. So you have to plug inside that formula the formula for the Segre class of the tangent bundle of a hypersurface. But if you have a hypersurface in the end, of course you have you are able to compute the Segre classes of the tangent bundle of the hypersurface using the standard exact sequence of the tangent bundle, and so the Segre class of the tangent bundle is just the Segre class of TBN. Maybe it's n plus 1 here, TBN plus 1, times the total churn class of the normal line bundle, which is just, no, you can express everything down that way. If you call small h the class of a hypersurface in Pn plus 1, then you have this for the expression of this total Surrey class and the Chern class of this total Chern class of the normal bundle is this. So plug this in. And now be courageous, so they have to do a rather subtle computation to end up doing the following. In the end, you can rewrite the intersection number as a polynomial in the degree. So not any polynomial, it looks that way. So it is a polynomial in the degree, d of the hypersurface, and you have some coefficients here which depend on n. Only on n. And also on the parameter epsilon that I have put here, but you can fix it to some adequate value. And let's assume I have done that. So here the only three parameters are d and n, actually. So you do that, and now there is some lemma, which we can attribute to Fujiwara. So here there is a trick which has been used in several places. For example, in the first paper by Diva and Mercaruso, they also used that thing. The lemma of Fujiwara tells the following: if you take a polynomial with real coefficient, let's write that as a0 t to the power n, etc. until an, with a0 positive, and also if you look at the absolute values of the ai, they are smaller than some constant, say, to the power n minus 1 times a0. Okay, suppose you have a polynomial like that, and then you can do the following exercise. Then, for t larger than 2d, one has that p of t is positive. Okay, so if you're bored, you can do this exercise. And the trick, I don't know if it's a trick, so, as I said, a rather subtle computation. Again, be able to have satisfying expressions for this qjn. But if you are courageous enough and you look at them in the eyes, so you can prove that this polynomial satisfies, which is written here, that the top coefficient is always positive, and also if you look at the other ones, so again they depend on n, but their absolute value is bounded by a product of the first one times some universal constant, say, times n to the power 4 to the power, again, n minus 9. And so this c times n to the power 4 plays the role of d here. Thus, if d is larger than, say, 2c n to the power 4, one has that the expression that is written here is positive. And this ends the whole proof. Okay, so I have 5 minutes in advance, but I don't see the point of continuing further, so let me thank you.
Are there any questions?
Yes?
I have a bit of a philosophical question. So,
yeah.
So you produce these deformations, you explain how to produce these deformations, and in particular, the O1 deforms and this bounded deforms. So,
Yes.
Okay, and then like summarizing, you have on the special fiber you have NEF, so you prove that you have NEF general, and then you have big by the mass. So I wonder, is it true that once you know about this deformation, you can absolutely forget the special fiber? Like you no longer.
Yes, somehow in this strategy that is the case, somehow because the holomorphic Morse inequalities, what they prove, where is it written? Oh, sorry, I have erased that. But what you can prove using the holomorphic Morse inequalities is not simply that the H0 has large growth, but rather that the H0 minus H1 grows quickly. So the true conclusion of the holomorphic Morse inequality is that the H0 minus H1 of this L times M, L to the power M, is larger than this coefficient then times this, and there are some lower. But here, H0 minus H1 enjoys a semi-continuity property with respect to deformations. So what this strategy proves is that on the central fiber you can prove that H0 minus H1 is big, and also then it will carry to the other fibers. So somehow if you have a deformation such that on the central fiber H0 minus H1 is large, then you can, as you said, only care about the central fiber. And again, so this deformation is a very important, I think, business in when you want to study jets, because they allow you to linearize problems. So in the article of Bérczi-Kirwan, it is done in a slightly different fashion using classifying spaces, which is, I think, another very interesting way of looking at that. I must admit I am more familiar with these risk deformation algebras, but in the end, what I want to emphasize is that it is something which is very important in this strategy to deform things to spaces where you can prove positivity, for example, of H0 minus H1.
I have a question. You had said for what happens if you take K larger?
Yeah.
One might hope that it would help.
So I think you can certainly do that and end up with another polynomial, but I don't know if it will help. For example, for hypersurfaces, it's if you use these holomorphic Morse inequalities here, this number tends being worse and worse as you get to higher stages of the tower. So as Erwan told 2 days ago, it is possible, for example, to prove that if you go to infinity in the order of jets, there exists holomorphic Morse, differential equations on the hypersurface. So this is a result by Joël Mercœur for hypersurfaces and Demailly for general varieties of general type. But you cannot use that to prove this existence. As k goes to infinity, you have to use. So you can do that in different ways, but if you focus only on holomorphic Morse inequalities, these ones are too coarse. So I think if you wanted to go in the higher orders, maybe you would have to use Demailly's versions of holomorphic Morse inequalities, the final one, using Demailly's holomorphic Morse inequalities, actually. Or maybe also the strategy that I use, the algebraic versions that I use to reprove this theorem for varieties of general type in the general case. But these are too coarse. So I don't know if, again, in the end, it boils down to doing computations. So to give you a clear answer, I would need to see the computation for myself and say, okay, this works. But